Hey everybody, it's Mr. Roy. I wanted to make a short video for you about these relative motion problems, these so-called boat problems, just to give you a bit more grounding in it, and we'll talk about kind of the theory of it and the approach to it, and some strategies, and then we'll also look at an actual problem and do some uh, problem solving with some real numbers. Now, we often tie these to like boats and crossing a river, but I just want you to know that the kind of physics we're doing here actually has super broad application. So we could be talking about planes moving through the air, which could be talking about like tensor forces within something, or we could even be talking about accelerating particles in a particle accelerator using electric and magnetic fields. It's all the same math. So adding vectors is a really broad skill, but we like to anchor it in something physical. So we have our boat problem when we talk about a boat moving across the river. It's something we can think about from our everyday lives and something we can actually more easily physically see. Okay, so I wanted to go to a nice little, we have a nice little simulation here for our boat crossing problem. And we can see that with, I just want to show you like a couple of different cases that we are going to have. We could have the very simple problem of where we have a boat that just goes across the river. In that case, the only velocity we care about, the water is still, the only velocity we care about is the boat. And this is our simplest version of the problem. If we know the velocity and we know the distance, we can calculate the time to get across the river. That's just a very simple motion formula setup. But we could, of course, add a complication. If we have a velocity to the water, it's going to go downstream. We can actually show our velocity vectors there. In this case, we've got the velocity in the y direction, that is the heading from our boat, the velocity in the x direction, that is the current, so our medium velocity, and then that shows our resultant vector as well. Let's run this and we can see it heads over across and heads to the other side. Now, interestingly enough, this took 12.55 seconds. If we get rid of the current and run it, you're going to find that this, no surprise, takes 12.5, well, in this case, 5.6 seconds. That's a little problem with the sim. It is identical. This time to get across the river is identical, whether because the current is perpendicular to that movement across the river. The current has nothing to do with getting across the river. It doesn't affect it at all. The only thing that matters is our heading across the river. So we can say, okay, time is independent of that. All we need to figure out the time across the river is that heading of the boat. That's all we need. We don't need to know the current at all. It actually doesn't matter. So our first situation looks like just a simple one like that. We also saw the situation where we wanted to not land farther downstream. In fact, we wanted to turn into the current so that we end up directly across the river. So we can actually turn ourselves here and we can see we could do something like this and run it, but that wasn't enough. The X component of our heading wasn't enough to stop us moving downriver. So we got to keep going until we end up with a right angle triangle. And we see when we have a right angle triangle that that's going to send us directly across the river. And you can see here is our nice right angle triangle. What's going on here is the X component of our heading is perfectly counteracting the current moving the other direction. So here we go. Let's run that one. And that's going to take us directly across the river. That one's going to take a lot more time because we're not pointed directly across the river, we're pointed upstream. So the component of our heading that is going across the river is smaller because we're not completely turned in that direction. So this is our next type of situation where we want to completely counteract the current. Again, we're doing SOHCAHTOA, right? We've got a right angle triangle. So in our first situation, we say, show the vectors, that's a right angle triangle. In our second situation where we want to counteract it, that's also a right angle triangle. Both of those we can use SOHCAHTOA. This one, though, we're going to end up using our sine ratio because we know the hypotenuse. This one, we're going to end up using our tan ratio because we know the adjacent and opposite sides. The trickier one that we looked at is what if we have it at a weird angle, like say it's, I don't know, like this, right? This can be a little bit of a trickier problem. So we want to have kind of a standardized approach to how we're dealing with this, because this one we're actually going to end up upstream. Our current is still in the nice X direction completely. We don't have to do much with that, but our heading is at a weird angle. We're going to have to use vector components for this. We're always going to be using vector components in situations like this, so let's get used to it and let's practice it. Okay, so let's talk about our overall strategy when we're solving problems like this. Okay, so we're talking these relative motion boat problems. And this is an example of the kind of problem we might end up with. I'm just going to take a little tea break here while you start reading and see what's going on here. A little bit of Earl Grey is keeping me going. Okay, so we've got a boat, 6 meters per second in still water. That's its heading, 45-meter wide river. Current is 2 meters per second. It's going west. So usually we're used to going east. Let's go west to, I don't know, keep it fresh. And then we have our kind of series of questions here. Let's just talk strategy. So our first step is always going to be, do we have any vectors at a weird angle? If we have vectors at a weird angle, then we're going to have to split things into x and y components. If we're dealing with a right angle triangle, we don't have to do that. But if we're not dealing with a right angle triangle and we got a weird angle, we got to split things into x and y components. That's how we're going to be able to move forward. Any vector at our weird angle is going to be x and y components. Our current is never going to be. It's always in the x direction. Step 2, we're going to take all of our x components and we'll add them together. And we're going to take all of our y components and add them together. Chances are you just have one y component. That's the y component of your heading. You're going to have two x components though. You're going to have the x component of your heading and you're also going to have that current. And so we're going to need to combine those two together. The example we showed before was when the boat is pointed really far upstream. We've got the x component pushing the boat upstream. We've also got the current pushing back on that, and those will cancel each other out to some degree. Now is the next part. We're going to do this on almost all of these problems, so we're just going to follow this. We got to calculate the time. The time is going to be the same whether there's a current or not. So we calculate the time to cross the river using our y velocity and our y displacement. And we know, since we're talking about uniform motion, we don't have to get into our accelerated motion formulas, right? We're just dealing with our velocity and our displacement and our time. So we're just using our standard uniform motion formula for that. Once we've got the time, we can take that and grab it and we're going to use it. So we're going to plug it in over here and we're going to say, okay, we got the time now. And we know our velocity in the x direction because we know the current, and there might be a component of our heading that's also in the x direction. And so we figured out what that is. Now we're going to use that overall velocity in the x direction, and we're going to calculate the distance up or down the river, how far it goes. That's our displacement in the x direction. Okay, so that's kind of our strategic approach towards solving these. Let's jump in on some of these problems. I'm going to take a little bite of cinnamon bun as we move to the next page, and you can kind of get yourself oriented to this problem, and then we'll jump in. Oh, cinnamon bun, delicious. Always so good. Okay, let's use our vectors here. Let's draw some. Oh, I got blue vectors. That's going to be really annoying. I'm not going to be able to see them here. Let's make them bright green. That should show up nicely on our river. All right, now that you're done hearing me chew in your ear, let's just talk about our directions here. Our current is overall going west, so we got to be prepared for that, right? Our current's going to be headed to the left, even though we're more used to seeing it go to the right. Okay, so we got a couple things going on here. How long does it take to cross the river if we go straight across? So let's draw our vectors. We're going, our boat, this is our heading, is going to look like this. We're aiming straight across the river. So far, so good. Now we're going to add in our current. Our current is going to go like that. Now our heading is 6, our current is 2, so I should make that a bit smaller. And let's label those ones. So this one's going to be 6, and this one's going to be 2, and then we're going to have our resultant vector, and it's going to go like this. Voila. And we're also going to have an angle in here. We might need to know that. That might be important. Not for this particular question, but we're going to get there eventually. So how long it takes to cross a river if it heads straight across. Now, I ask you, what vectors are important for getting across the river? And I want you to like nod or shake your head. Does the current matter for getting across the river? And we all shake our heads. No, it does not matter. Current has nothing to do with it. You can't get across the river by relying on the current. The only vector that matters for getting across is our heading right here, because that's the only one in the y direction. So that's the only one we have to concern ourselves with. So this is actually a pretty straightforward problem, right? We'll say, okay, the velocity in the y direction, in this case, it's our heading. That's going to be equal to the change in displacement in the y direction divided by time. It's just our simple motion formula. Let's rearrange that. Time would go up here, and then we'd have our displacement in the y direction divided by velocity in the y direction. So for our time, we're going to say it's 45 meters to get across the river, and our velocity is 6. So 45 divided by 6, that's going to give us our time. We end up with 7.5 seconds. Okay, let's put a box around it. We're going to use that 7.5 seconds, and we're going to carry that forward to our next question, because the time doesn't matter whether you've got a current or not, it's still the same amount of time to get across. Let's jump in on our next one. Here we go. Okay, same as before, but a little different. Let me actually grab this picture here. I want to take that with me as we go to our next page. All right, lovely. We'll just cover that up right there. Okay. So we have our vector showing, and it says how far downstream it lands using the heading from A. So how far downstream does it go? Now I'll ask you a question, and I'll say, which of these vectors matters for heading downstream? Does the y component, that's our heading with the boat, matter for getting downstream? And we all shake our heads, no, it doesn't matter. The only one that matters for going downstream, because it's in the x direction, is this one right here. The current is the only thing that matters. And we know how much time it takes, right? So let's jump in on this. We're going to say, how far downstream do we get? Here's our point across. Oh, that's not going to work in blue. Here's our point across the river. We're going to move down some amount. So that's our change in displacement in the x direction. So I'm going to say, okay, if I want to figure that out, my velocity in the x direction is equal to my displacement in the x direction over time, right? That's just our standard uniform motion formula. And we say, okay, we want our displacement. So I'll multiply both sides by t to move it up to the other side. So we rearrange our formula. We say our displacement in the x direction is our velocity in the x direction times the time. So our velocity in this case is 2. Our time we calculated in the last problem was 7.5 seconds. So we end up with 15 meters. And let's put a box around that to show we got our final answer. Okay, so it ends up 15 meters downstream. Now this would be, getting to be a good answer, but you may have noticed, hey, Mr. Roy, this needs a direction to it, right? Because we didn't say the direction. So we're going to add that, and we're going to say our direction is downstream. We'll put some square brackets around that and then finish our box. Okay, nice. We've done B. Let's jump in on our next one. This one asks us, what's the angle the boat must head in order to travel straight across the river? So I'm going to have to redraw my vectors here because I'm going to be going in a different direction now. Let's go back to our nice, lovely green color. So I know that my current is going to look like this, right? That didn't change. So here's what I need to do. I'm going to need to have some type of heading that's going to make sure that when I travel across the river, it's traveling in a straight direction. So my resultant is going to have to look like this. My resultant vector, when I add my two velocities together, has got to be going straight across the river. So my boat is actually going to point into the current, and it's going to move straight across the river, just like that video we saw in class. So this has got to actually be my heading. I got to go like that. So the heading and the current add together to make a vector moving straight across the river. So I need to know the angle that the boat is going to make. So I'm trying to find the angle here. I'm going to call this theta, and I'm actually going to call this beta because we actually want to know the angle relative to the shoreline. Now, we can put in some numbers here, right? This one is 6 and this one is 2, just because we have those from the question. So we say, let's do some trigonometry because we have a right angle triangle. I know the opposite and the hypotenuse. That's a sine relationship, right? So I'm going to say sine of that angle theta is the opposite side over the hypotenuse. So that means theta is going to be the sine inverse. I can put in my opposite, my hypotenuse. My opposite was 2, my hypotenuse was 6. So I plug that into my calculator. That's some bleep, bloop, bleep, bloop. I end up with 19.47122. I'm going to go to 5 decimal places just to kind of make sure I don't miss anything there. And that's in degrees. Now I want to know beta, right? Because beta is the angle I can say relative to the shore. So I'm going to say that's going to be 90 minus this 19.47122. So I can say my angle beta is going to be 70.52878. And I can write my kind of therefore statement. So the angle the boat must travel, I'm going to say it is upstream 71 degrees. If I round that off to 2 sig figs relative to the shore. I'll put a box around that to show that's my final adjusted answer. Nice. So you could say 19 degrees upstream. That's okay too, because you are 19 degrees from going across the river. So you're pointing across the river and then you turn upstream 19 degrees. But I think the first one that I put the box around is a little bit clearer. Okay, let's roll on to part D. This one says a boat which can travel 6 meters per second in still water is moving 45 meters in a 45 meter wide river whose current is 2 meters per second. Determine how long it takes to cross using the heading from C. So we got to go back to C and we're going to say, okay, I need to know how long it's going to take to get across. Let's actually copy my picture from this side here. And we'll paste it right here. Cover that one up. Okay, so we want to know how long it's going to take doing this to get across the river. So the vector that is moving us across the river, our actual velocity in the y direction, is this one right here, the red one. Okay, that's the one that's going to get us across the river. That's the x component of our heading in this case. It's our resultant vector. So that's the one we want, but we don't actually know what that is, right? We know we can say that's our velocity in the y direction, but we don't know what the value is. So we need to do some math for that. Oh, it's a right angle triangle. That's just Pythagorean theorem, right? So we're going to say, okay, the hypotenuse is 6 squared, and then the other two sides, velocity in the y direction squared, and 2 squared. So our velocity in the y direction, if I kind of simplify that, is going to be the square root of 6 squared was 36, minus 2 squared was 4. So that's the square root of 32. So when I actually work that out, that's 5.6568 meters per second. Okay, so that's how fast we're heading across the river. So now it's just a simple basic motion formula. We say, okay, well, we want to figure out how fast we're getting across the river there. So we'll say, okay, velocity in the y direction is displacement in the y direction divided by time. Let's plug in our values. Actually, let's rearrange this formula first. That's going to make our lives a little easier. So t is there. We've got delta dy over the velocity. I'll move up here to get myself a little more space. And we say, okay, our displacement in the y direction is 45 meters. That's to get across the river. It's 45. And our velocity is 5.65685. So 45 divided by that, we work that out. We end up with 7.95495. Let's round that off. For sig figs, that's going to be 8.0 seconds, and we'll put a box around it. So this time it takes us 8 seconds to get across the river. A little bit slower. Previously it was 7.5, but we're no longer aiming or heading right across the river. We're aiming upstream a little bit. So we're not, our component of it that's pointing across the river is not as big. So it's going to take us a little bit longer. Okay, our final one. This is the type of problem that we were having a lot of trouble with in class, where we had a vector at like a weird angle and we needed to figure that out. And I think there's one in your notes that describes a weird angled vector heading downstream and then the current adds to it. That's a little easier than if they're opposed to one another, which is the question from your Check Your Understanding 4C that people are having a little bit of trouble with. So let's try one that is similar to that. Okay, so this is going to be a little tricky. This is a good challenge problem. It's valuable for us to wrestle with challenging problems. That's good for us. That's important in our learning, that we want to challenge ourselves. So that's what we're doing here. Okay, so where does the boat land if it heads upstream? And remember, the current is flowing west in this case. So upstream would be to our right on the screen. Where the boat lands if it heads upstream at 72 degrees relative to the shore. Okay, let's try drawing first, right? So we'll say, okay, let's get our vectors here. I'll get a nice looking green one. This is going to be heading upstream. So I got a point at 72 degrees relative to the shore. So that's actually like pretty far. Like this is close to the shore. This is far. This would be 90. So 72 is like, I don't know, like right there, I guess. And now our next vector is our current. We need to add to that, which is 2. Now here's the challenge. I don't know. Does my current go like way over here? Does it go here? Like I'm not totally sure when I'm doing my drawing. So I'm just gonna, I don't know, I guess put it like that, I guess. Now this is not going to make a right angle triangle. You might be tempted to draw a right angle triangle and be like, aha, right angle triangle, pretty close, right? No, this is not a right angle triangle. Or, I mean, I guess technically it could be, but I don't think it is. We can't assume it is, so we got to draw a resultant vector kind of like that. Now this is a little bit tricky. We want to decompose our vector that's pointing in a weird direction into x and y components. So we're going to do that. I'll make this green so it matches here. So because our current is in the x direction only, so that's fine. It's good to go. But this one has got a component in the x direction. That's going to counteract the current. And it also has a component in the y direction. That's going to move us across the river. Okay. So we got to dive in on this. Now we can give those some values, right? This one right here, this is, let's put on our angle here. We said that this was 72 degrees relative to the shore. So this side here, it's adjacent to that angle. So this is going to be, oh, let me put my magnitude on here. We know this is 6 and this is 2 still. So we know this is going to be 6 cosine of 72 degrees. And what's that work out to? That's 1.85410. And we're going to call this our velocity in the x direction for this particular vector, for the heading. But we can't forget there's also the current that's going to counteract that. It looks to me like the current is bigger. 2 is bigger than 1.85410. So that means the current is going to win and our boat is actually going to drift downstream. Okay, now let's do this one over here. This one is going to be 6 times the sine of 72 degrees. So that's going to be 5.70634. And we're going to call this our velocity in our y direction. And it's the only velocity in the y direction. There's no other y velocities here that we need to worry about. Okay, so let's do this in kind of a set order here. Let's go step 1. Step 1, we got to find the time to get across the river. So the only thing that matters for getting across the river is this velocity in the y direction, 5.70634 meters per second. That's the only one that matters. So we're going to say step 1 is find the time. Let's do that right now. So we'll say, okay, the velocity in the y direction is equal to the change in displacement in the y direction divided by the time. So we put our values in. We know this one is, we already calculated it. It's 5.70634. And we know our displacement is 45 meters. We want to know our time. So we'll move our time up. We'll divide our 5.7 down. We end up with 45 divided by 5.7 and change. And we end up with a time of 7.88597 seconds. Okay, so that's our step one. That's how long it's going to take for this boat to get across the river. We're looking at the y velocity. There's only one of them in the vectors that we're adding together. So that's the one that we use. Easy. Okay, let's go step two. We're going to find our velocity, our total velocity in the x direction. Now, why did I not just say Vx? Well, because that's only this one here. There's also the current. So we got to take into account that there's the two of them. So I said the velocity in the x direction total. You could have labeled that however you want, but as long as it's clear. So I'll say, okay, the velocity in the x direction, the total one, is going to be equal to our current of 2. Now I know the current wins, so I'm going to call that the positive one. And we're going to subtract the current upstream, 1.85410. Sorry, that's slightly messy writing. We subtract these two, we get this. This is meters per second, right? So this is like 0.145. So this is like 15 centimeters a second, right? Pretty darn slow that we're drifting upstream. We're barely drifting upstream, but we are a little bit. Okay, now let's do step 3. For step 3, we're going to find that knowing that we are drifting downstream and knowing that it takes 7.9 seconds that we're doing that, let's find our displacement in the x direction. We're going to be drifting downstream. So let's find that. So that's, again, uniform motion, right? Our velocity is displacement divided by time. We want to find displacement, so we'll rearrange our formula. Let's plug in our velocity. We found that previously, so that is a really small number. And our time, we found that previously too. Multiply those two numbers together, and we end up with 1.15056. So I kind of ran out of room here, so I'm going to move over here. I'm going to round that off, and I'm going to say, okay, my displacement in the x direction is 1.2 meters, because we round out to 2 sig figs, and our direction is going to be downstream. Okay, so that's one of those tricky problems. I hope this helps solidify your understanding. Practice makes improved, right? So we got to put in the reps and we got to challenge ourselves with these tough problems. So give these a try. Come see me if you need a hand. I'm always happy to help. Good luck, folks. Talk to you soon. Bye for now.